Alrighty. Guys, let's talk about several announcements first, quickly, okay, and then we'll get to the topics. I'm not sure if you noticed that the exam day has been posted on the register website. It's rather early, December 9th. Our last class will be December 4th, which is Tuesday of that week. It's going to be Sunday of that week. We're going to have the exam, 7 p.m. What I would plan to do, I'll try to hold maybe at least one review session for you guys. Maybe it can be, let's say Tuesday is our last class, maybe Thursday and Friday, we'll see, okay? To see, depending on how much you need it, okay? Also your exam schedule. We'll talk about it. The midterm results, I'll make it available to both pick up the paper and also you will see the marks on Thursday. I'll give you more details, but Thursday you will see all the results. For lab number 3, because it's somehow related to lab number 4, you already see the marks for the report. But for the programming part, oh sorry, you don't see the report yet, sorry. I'll make the report marks available a little bit later. But for the programming part, I'll make it available by early Friday. Okay, so at least you can get some feedback on that. The code part, yeah, the programming part, yes. And then for the projects, I will release that by next Wednesday. So from next Wednesday's lab session, you can start working on the projects. Okay, you got 3 weeks for the projects. That's the plan. Okay. Okay, let's go back to our discussion about visitor. Let's recap very quickly what we said last Thursday. Basically, the first part that we talked about was based on the problem we are trying to solve. We're trying to solve a little expression problem, right? You want to do things like a 247 and also 247 plus 5. So how can you model such expression structure? So we apply what we learned from last time, the composite pattern over here, right? So that one I wouldn't repeat. You can watch the recording if you have question. Now, let me just review very quickly the open-close principle that we talked about. The open-close principle, again, says the following. For you as a designer, you have to decide which part of your system should be open, which means if there's any extension or modification, the open part should be changed. On the other hand, there should be other parts of your system that should be declared as closed. That means that if there's anything that should be changed for extension, the closed part shouldn't be the part to touch. Okay, open and close. Now, let's apply this open-close principle to our particular small expression problem. So there are 2 aspects for our small expression problem. One is about the syntactic structure for our language here. Let's, for the moment, only assume we only got constants and also we got additions. So these are the only 2 components for the structure. That's the first aspect. And the second aspect is so-called operations. What kind of operations can you perform on your expression language? It can be evaluates, it can be printing out prefix, printing out postfix, and it can be type check. So these are the 2 aspects. If you want to apply the open-close principle, you got many options there. Which one to take is completely up to you, your judgment. However, for the visitor pattern, we have to make sure we choose the open-close decision in a particular way. Otherwise, the visitor pattern should not be applied. Okay, let's review that very quickly. 2 possible open and closed decision could be, number 1, we can say the structure itself is open, which means we can add any subclass over here as a new syntax structure, for example, multiplication. Okay? On the other hand, we should not expect to add any new operations over here. That's the first option. Okay? However, this option here is not good for visitor pattern, as we'll see. Okay? Just keep that in mind. We'll review this aspect very soon. And the second option here is really important. The second option over here tells you the structure should be closed, whereas the operation should be open. So what does that mean? If you as a designer commit to this option here, that will be good for the visitor pattern. And what does that mean? That means you don't really expect any of the structure to be extended. That means you want to stick with constant, you want to stick with addition. You don't expect any more operations. You don't expect any more structure. On the other hand, you can add as many operations for the language as you like. For example, I might add another one, maybe generates Java code, for example, or generate MISP code, like what you learned in 2021, assembly code, right? So that will be the second option there, which is exactly this application context for visitor pattern. Yes?
To clarify, so for the open close principle in version 2,
Yeah.
structure is going to be the expression in the composite?
Correct. So the structure part for the expression problem will be the composite, which means the syntax, right? That's how we handle the syntax for the.
Oh, is it just composite? It's not structure, it's not expression
Yeah.
as well?
So you can see that the way, okay, again, if you look at the whole thing over here, that's composite pattern, agree? So this composite pattern only solves one aspect of the problem, which is a syntactic structure for the expression language. However, if you only get a syntax, there's no use. You want to apply some operation. For example, if I give you 241 plus 3, this is written invalid syntax using this expression language. However, you can do various operations on that. For example, if I say I want to evaluate, that should really give me the value of 244, right? If I say I want to print postfix notation, that should really give me 241 and 3 and plus. That'll be another operation to apply. If you only get a structure over here, it's only static. It's only a structure like a tree over there. But the operation will do something more to it. So two aspects over here.
The structure is going to be the syntax of the
Just the syntax for the language.
result, right?
Okay, correct. And the operations would be something you can think about. Operation will be some kind of traversal over the tree, some kind of traversal. Yeah. Okay. Guys, any question about this? It's a very quick recap from Thursday. Okay, ready for the visitor? Okay, let's now go to visitor. Let's see now a very important assumption which I'll revisit again at the end. You have to know that this is this decision, this is the application context. Application context of the visitor pattern. Okay, that's really an important thing, number one. But we'll see. You don't have to memorize it. Once you understand the visitor pattern, you will see how naturally that would be the decision to make. Okay, okay, let's go to visitor pattern. What I would do is I'll just go over some slides, and then we'll go over architecture. We'll go over how you can use the visitor pattern, and then we'll talk about how you can implement that, and also see some runtime structure for that. Okay, so let's go over some slides. So we got a separation of concerns. So we got language constructs, we got operations. And the way we solve the language construct is by using the composite pattern, right? So now we're going to see how we can solve the operations problem. Okay, we'll see. And then we just decouple these two set of classes. You can imagine that eventually you can put all the classes for language construct in a separate cluster, whereas all the classes for operation in another cluster. But you will see architecture diagram. And open-close principle, okay? What would be closed for visitor pattern? Basically, closed would be the language construct, which means it would be violating certain design principle if you try to extend the structure of the language by adding a new language construct. On the other hand, what's really open for the visitor is you're open to add any language operation as you wish. You may want to say generate assembly code, generate C code, generate Java code. Those wouldn't violate any design principle. Okay, just keep it in mind. Okay, so this is where it can be applicable. Okay. Now, this is architecture, but we'll go over the detail. Okay, I would say it's definitely more complicated than what we have seen so far, but let's go over the details. Okay. So that's don't worry about the code over here just yet. So this test code we'll go over in detail in just a moment. Okay, let's focus more on the design architecture over here. So there are two clusters. One cluster is about expression language over here. I'll try to make the PDF for the diagram available for you as well, maybe after today's class, so you can also study that. Expression language is the syntax construct for the composite pattern. Okay, I'll go into detail. And we got another cluster called expression operation. Okay, that's going to be the various operations we'd like to apply to the construct. And let's look at the expression language cluster, which you are more familiar with. Okay, we still got an expression class, which is deferred. We have the composite class, which is also deferred. Also, we got constant, which is a direct descendant of the expression, right? It's a basic components. Also, we got the addition over here using multiple inheritance. That's going to be a descendant of both expression and composite, right? That's what we learned. Now, what's new? The new thing is a feature called accept. Okay, let's have a look at that. Accept. And at the level of expression, the accept feature is simply deferred. You can see that there's a star over here. It's deferred. which means every descendant class of this expression class, they have to implement this particular accept feature, okay? But it's incredibly easy how to implement this. We'll see that in just a moment, okay? Now you can see that accept feature over here, what's the argument type, parameter? It's taking one single argument of type visitor. And where is visitor? Visitor is exactly over here in the right neighbor, but we'll get to visitor in just a moment. Okay, so you can see that accept feature is inherited and must be implemented in both the constant and also in the addition. Okay, so you can see the visitor, the accept feature over there is plus effective. Also here is also effective. Okay, so far so good. Okay, we just talk about architecture, which means if you want to adapt whatever composite pattern you might have for your language structure, number one, you have to define this accept feature as deferred in your expression class or whatever application class you might have at the top level. And then try to make the accept feature effective at every descendant class. Okay, that's about this cluster over here. Now, here comes the new bits, the essence for the visitor. Okay, so now I'm going to use a different color for highlight. So we have on the right-hand side, under expression operations cluster, we have a class called visitor. And that one there is also deferred, which means we may add descendant classes as we wish. Okay. Now at this point, we only got 3 descendant classes, which means we only try to support 3 different operations on the language. So what are they? We have one class, which is effective, called evaluator, which will try to evaluate whatever expression you have. We got another effective descendant called pretty printer, which will just pretty print. That's an infix notation. Doesn't matter, just for example. And also we got another one plus called type checker, right? Which means if you try anything like, for example, later on, if you have 234 plus maybe a string A, that shouldn't be type check, right? Things like that, okay? Okay, we got 3 effective descendants over here, but what about the features to declare? Okay, now here comes the tricky bits you have to remember. I want you to have a look at, first let's do some simple counting, okay? Basically, you can see how many features do we have. Let me just make it a little bit smaller. So we have one feature over, oh, that's not a good color. How about blue? One feature here called visit constant, another feature called visit addition, okay? Let's just worry about the name, okay? Can you see any connection between the names of the features over here to the classes on the left-hand side cluster? Yes. Expression, yes, exactly. So this is rule number 1. For every effective descendants over here, this one here, and this one here, okay, I'll put it here. So these are the effective or implemented effective descendants of the expression class. For every one of them, you have to create a visit feature. I'll put star here, which means the name depends. Visit feature in the visitor. That's rule number 1. Okay? Now, so that's why you can see for constant, I'll make it more visible to you. For the constant class over here, we have something called visit constant over here. On the other hand, for addition class over here, we have a feature called visit addition. And it shouldn't be too surprising to you. What about the type for the parameter for each visit feature? Well, for the case of visit constant, we got constant. For the visit addition, we got addition. Okay? That's about the visit. Guys, any questions so far? Okay? So these are still deferred at the level of visitor. Yes, question?
You're probably going to get to this, but I don't quite get the...
How to implement them?
Yeah,
We will get to the implementation. How about just bear with me? Yeah. Because I don't think we should jump right into the implementation just yet. Yeah.
I don't quite get the abstract connection between having to have an accept method, but at the same time also have a visit.
You will see. You will see that. So the question really was, you cannot really see the connection yet. You will see them. Okay. Once I show you a little bit of code, we'll see that. That's actually the beauty for the visitor. You don't really see too much connection there, but somehow once you just call the accept feature on a particular expression, they will do everything for you from there, recursively. Okay? I will get there. One more thing to mention, you can see that for every effective descendants of the visitor over here, we will be forced to implement every defer feature at the visitor level, right? Visit constant, visit addition. For example, you can see for the evaluator, you have to implement visit constant and visit addition. And also for pretty printer, you will have to implement visit constant and visit addition as well. So one thing to know, just at the abstract level, okay? Can you just tell me from the conceptual point of view, I want to highlight these two features and I want you to try and answer me. I want you to look at the visit constant over here, visit addition over here versus the visit addition over here. They are both called visit addition. Conceptually, how are they different? Oh, I'll just see if anybody want to say? Yeah. Anyone want to try? The question is, let me repeat the question. You can see in both evaluator and in pretty printer, or even also in type checker, we got visit addition, the same feature name, the same feature argument type, the same. Conceptually, are they the same? I heard no. Okay. How are they different conceptually? Anyone want to try? Yes.
So what does the evaluation, the argument does the printing?
Yeah, somehow you can see the context where we declared is different, right? One is declared under the context of evaluation. One is declared under the context of pretty printing, right? For example, let's say this. Conceptually, if you think about over here, if I have an expression like this, let's say 234 plus 2, okay? And now, if I say, if I have some, let's sketch the idea. Let's say eval is of dynamic type evaluator, okay? When I say eval dot visit, let's say this is expression E. Eval dot visit addition, I will say visit at, and then I pass expression E over here. Versus, if I got another one, let's say pretty print, let's say PP, standing for pretty printing. Let's say the dynamic type for this particular object is of type pretty printer. Okay, if I had a PP dot visit addition over here, and with the same objects, right? You can see that we are calling the same feature over here with exactly the same argument objects, but the context object over here are different. Depending on what the dynamic type is, it's going to do something different. Again, dynamic binding, okay? For example, for this part particularly, eval.visit at, what it's going to do, you simply go to eval. So that will give me 236, right? On the other hand, for this one over here, it's going to do pretty printing. For example, it might just print postfix. It might just give me a string, and then 234 and 2 and plus. You can see the same expression objects, but the consequence will be different, depending on what the dynamic type is for the visitor. Okay? But the beauty about the visitor pattern is you should never ever have to write things like eval.visit at and pp.visit at. You should never have to do it. It may not make sense to you, but let me repeat and then just keep that in mind. For you as a user for the visitor pattern, ironically, you should never expect yourself to write something like to say eval, which is a visitor object, eval.visit at, or pp.visit at as a user. You don't have to. So what do you have to write then? I'll show you in the test, okay? Now let's go over the test code. For the purpose of this particular page, I just want to show you how you can use it, okay? And then later we'll see how exactly you can implement it and we'll trace the code, okay? That'll be the flow. Over here, let's have a look. So we got this particular test over here. So we got add C1, C2 of type expression. And also we got V of type visitor. Right? You can see programming to the interface, but not to the implementation. Expression over here is as general as we can have. And visitor here is also as general as we can have. Right? So now, you shouldn't be having too much trouble of tracing 4, 5, and 6, right? What are we trying to do here? It's basically composite, right? What we are doing here is we are trying to say create constant C1 and C2 of different values, 1 and 2 respectively. And then we create an addition, adding C1 and C2 to be left and right. Right? That's basically what we're trying to do. And then we also create a evaluator as a visitor. So the dynamic type for V is actually evaluator. Okay? Okay, I'll trace this in just a moment, but let's not distract the flow. The only thing for you as a user to write, as opposed to things like this, all you gotta write is something like this. Add.accept V. First of all, does it compile? Let's figure out. What's the static type for add? Expression. Does expression define a feature called accept? It does, exactly here. And the type is simply visitor. And now, what's the static type for V? Visitor. So it matches. That will work. And let me just preview a little bit. This, as we trace this particular line of code, is going to in turn calling lines like this internally. But for you as a client, you don't have to write things like this on the right-hand side. For you as a client, all you got to do is as follows. You do things like from line number 4, 5, and 6, you create your expression objects, in this case just just add. And then you simply say accept. For me as an expression object, I want to accept this particular visitor. Once I accept it, the visitor is going to do everything that's required under the hood. But we'll talk about what exactly it will do. Not yet. Right? I'm just trying to go one step at a time. Right? That's why visitors sometimes can be confusing at the first, but it's actually quite beautiful, the pattern.
Would you be able to explain, so what exactly is the point of it, and how does it do it automatically for you?
But we'll answer all your questions in just a moment. Okay? Okay, let's just see how we can use it first before we know how to implement that. I'm sure you're curious about how to implement that. Okay, first, okay, line number 7 is basically what you have to write. Basically, we have created an expression object called add, and then we say accept this particular visitor, which is V. And V is of dynamic type evaluator, which means we want to do evaluation. And after this, we can simply do a cast from V into evaluator and say eval, right? We learned about cast. And then we can say after accepting V as an evaluator, eval, the value will be simply 3 because we are basically adding 1 plus 2. So that means the value should be 3. Okay, that's the overall picture. Guys, any questions? Except you want to ask me how to implement that. We'll see that, okay? Yes?
Is it like for an operation that doesn't really depend on what the specific type of composite node it is? Could you make it so that the visitor only has a visit composite method?
I would say, okay, the question is really about should we actually try to treat, okay, basically you're still talking about how we implement the visitor, right? So, okay, let me just say this for this particular page. When we try to implement every descendant of the visitor, we have to implement every visit feature. And every visit feature should correspond to a particular component in the hierarchy for the expression, right? I would say you may have to treat them case by case. It's really hard to give you a general account about how to implement them. What I can say is typically, let me just say that first before I show you the implementation, okay? Typically, let's say if you want to do evaluation, if you want to evaluate a constant, it's very easy, whatever the value it is. It's not recursive. On the other hand, if you want to do the evaluation or you want to visit a particular composite operation, in general, that should be recursive, which means recursively visit the left-hand side, recursively visit the right-hand side, combine the result. Pretty much like how you would do for a binary tree, right? Questions or?
My question was, when we do add.accept,
Yep.
what are we checking? Like we're checking the type.
When we do add.accept, basically, okay, based on what we learned about dynamic binding, what you call add.accept. Okay, let's talk about it very quickly since it's an important thing as well. Let's talk about this line here, okay? Let's talk about this line here again. When I say add.accept, we have so many accept over here. You can see that we got, I'll highlight. We have accept over here, deferred. We have accept over here. We have accept over here. We got 3 different accept you may call, right? So now, at this line over here, which one are we calling? The one under addition, right? Because of dynamic binding. Because we know that at this point, add is of dynamic type addition. So that means the version for accept that's under addition should be called over here. Okay? And now the question is, how exactly is the accept feature for addition defined? We'll see. Okay? Okay. Guys, any more questions abstractly before I go to the code? Again, I would say the most important thing is for you to understand things from the architecture first, so you get a big picture before getting into the code. Okay?
I'm still a little confused about the naming of accept. Like,
Yeah.
how does the user know what they will get out of calling that method?
Okay, question. Okay, good question.
Everywhere.
It depends on the context object you're talking about. For example, let's say here, you can see we got 3 expression objects over here. We got add, we got C1, we got C2, right? All of them are expression. We can definitely say add dot accept, and then give the V over here, right? That's what we are doing here. And we know the result is it's going to somehow give us the evaluation result, which is 3. On the other hand, we can also say not add. We can also say C1, which is a constant over here. C1 dot accept. And we pass the same evaluated object over here. That means we're only trying to visit this particular left child. And that will give us the value just 1 rather than 3. And then we can also try to say C2 dot accept, in which case we can also pass the same evaluated objects, which will give us 2. So that means you can get a little bit hints about how we can implement the accept feature or visit feature. You have to recursively accept the left child, recursively will visit the right child, and combine the result together.
My question is, the user knows not by the name of the method, but by the objects that they use.
Correct. So that's the beauty about OO, right? Because all is about the dynamic type for the dynamic type of the objects, context object. All right, let's now go to this slide over here. You know what? This part is really about visualizing line 4 to line 7. How about we just go to the visualization directly? Basically, I just want to see if you know how to visualize what's happening here. I assume you know. I'll show the diagram directly. Okay, let's not waste time. So what I would do is, let's now go over. Now, you can see from line number 4 to line number 7, we're basically creating 1 plus 2. 1 plus 2. And at the runtime, it's going to correspond to something like this. So we have an add object over here, which is addition, the dynamic type. Also, we got left child and right child. The left child is a constant object C1, a constant, and then points to, it's actually got a value 1. And we also got the right child over here, and it's the same as C2, which is another constant, and the value is 2. Okay, follow? Let's say that's the simple expression we are trying to visit. Okay? And then what we are doing is we are simply calling add.accept V, as I said. But now we're going to see exactly how it is going to work. Okay? And at the same time, we also got another visitor object called V. V is of dynamic type evaluator over here. And the value over here, we don't know what it should be yet. Don't know yet. Okay, that's kind of the outline for this diagram over here. But we're going to see exactly how we can do it. Okay, let me clean the diagram quickly. Okay, so now here, these are the code for both the visitors and expression. But we're going to go over line by line. Okay, so first of all, let's see exactly how we implement the accept feature. Let's see that first. And there are 2 accept features we have to implement because we got 2 descending classes that we talk about. One is basic, the other one is composite, right? Let's see that then first. So we have one constant class over here, which is a descendant of expression, direct descendants. So that means this is a basic components. Okay, you know the idea. On the other hand, we also got another class called addition, and it's multiple inheritance. You're going to inherit from expression and composite. Okay, so now both of them got the accept feature over here, And then we got v visitor, the same. Now, as I promised, it's incredibly easy to implement the accept feature from the expression side. So what do you say? Well, all you got to say is, since I'm now, I will use a different color. Since I'm now in the context of the constant class, remember for every expression descendant class, we need to have a visit feature in the visitor side, right? So we want to make sure whatever v it is, we pass as arguments, call v dot visit whatever the context class is, and then pass the current expression objects. Okay? Current's like this in Java. Hopefully you know that already by now. Okay? That's about how you implement the accept feature for constants. What about the accept feature for addition? Similar. Because now, okay, we still have the v as a context object over here, and since now we are under the context for addition, so we'll say visit addition and pass the current object, and that's it. So the way we implement the accept feature is very routine. So the real intelligence will go into the visitor feature. Okay, we'll go there. So far so good? Okay. So now let's have a look at the visitor. Okay, again, for the visitor feature, let me use orange here. So visitor over here, that's a deferred class, as you can see. And we got visit constants, we got visit addition. And also for the constant, we got C of type constant. And for addition, we got A of type addition. Okay, they have deferred, okay, at the level of the visitor. Now, let's see how we can implement these. What I chose for now, I chose this particular descendants of the visitor, just this one here. Okay, it will be exercise for you to think about how you can implement the other two descendants. Okay, let's just do the evaluator, which is good enough. Okay. Well, we know that first of all, this evaluator inherits from visitor. That means we have to make two features over here effective, right? The first one will be visit constants, which will take constant. And we'll also do visit addition, which will take addition. One thing to note. I want you to notice that the way we declare the types over here for the arguments, we don't simply do expression. Did you notice that? Over here, you can see C is of type constant as opposed to expression. And A is of type addition as opposed to expression. Right? There was a reason for that. What's the reason?
Because when you're actually calling them the different constant class, you're using current, which is this or that.
It's more than that. Well, it will still compile. I'm saying that what if I put expression here? It will still compile. Nothing wrong with that. My question is, okay, how about let me test your knowledge about inheritance. Let's just say for this one here, when I say visit addition, rather than having addition over here, I simply put expression. Just for this feature specifically, do you think it is going to compile? Are you sure? Well, most likely wouldn't compile, right? Otherwise, why would I bother asking you, right? Okay, if you don't think that will compile, which line or which expression?
For that one, it should be like expression as well with the fruit class visitor.
Which one?
Like in the visit.
Oh, you mean which one? You mean this one here?
No, in the deferred class visitor.
Yep.
Visit addition.
Yeah, that's okay. Yeah, sure. Yeah, that's what I meant. Yeah, sure. Let's change that to expression as well. Okay, guys, let me repeat my question again. It's really important because you may want to use it for your projects. Would that be a big hint? You might want to use it, okay? Okay, let's see. Wow, now okay, more people paying attention. That's good. Good, okay, now let's see over here. When I declare visit addition here, what about I only say expression? As general as I can over here for expression, as opposed to the descending class addition. So that means visit addition and also expression over here. So now, if you consider only this feature here in isolation, do you think this fragment of code will still compile? If you say no, why would it not?
The left and right.
Aha, exactly, right? Remember, yep, that's exactly right. It wouldn't compile because the compiler would not be so happy if you simply do left and right over here, right? Because the static type for A will just be expression. And what do we define in the expression level? Only accept. Left and right is only defined at the composite level, right? You can get around with that by using cast, but you don't want to do that for every composite descendant class, would you? Right? So that's why we made such design choice. Okay, keep that in mind. That's an aside. Okay. Okay, let's change it back. So now we do want to use. When you watch the video, you will see the change I was trying to make. Okay, I'll just put it back. Okay, so that should be constant. That should be addition. So now let's see how we can implement the visit constant and visit addition feature. Okay. Now, as I said before, the general principle, the only one I can give to you will be, when you talk about a visit feature that is to do with basic components, I would say that one should be rather straightforward. Usually it is not recursive, usually. Okay? So now, how do we visit a particular constant objects? If you're given a constant, how can we visit it as far as evaluator is concerned? How do we evaluate? Well, just return its value. Oh, by the way, so I'm just declaring one particular attribute value for this evaluator. You can define whatever attribute value you like or queries for your particular visitor. Now, let's say for evaluator, we just got a value just called integer. Okay? So now that means whenever I say I want to visit a particular constant like over here, remember I said you can say C1.accept V, right? Now, when I say C1, what's C1? C1 over here is simply just a constant of the value 1, right? In that case, I can simply just pass whatever value it is for the constant to the value for the evaluator. So that's how I evaluate, okay? Question about this? Okay, now let's go to the other possibility over here. Let's say we want to visit addition, where addition is simply a composite, which means things might go recursive. I would say think about visitor pattern is more like a general tree that you learned from 2011. Not necessarily binary, maybe just general tree, okay? You know what a general tree is, right? You know what? Go to my lectures page, go to 2030. I talked about it last year. Okay, just go there. Well, I think you're teasing me. Of course you know what a general tree is. Okay, all right. So now, let's see how we can do this one here. Visit addition, okay? The idea is very simple, okay? In general, if you're given, I'll just draw the picture very quickly, I'll erase it. If you have some composite expression in general, expression like a tree, and that one there has maybe different number of children, I'm just talking about general case, not necessarily expression. Each one of them can just be a subtree, right, for the expression. So now, if I say I want to visit this particular expression tree, so what does that mean? That means if I want to visit, let me just use highlighter here. I want to visit this particular one, I should first of all visit the first child, visit the second child, visit the third child, and somehow combine the result for each visiting into the result for this particular level. Make sense? Okay? It's pretty much like how would you do it in order traversal? Visit the left child, visit the left subtree, visit the right subtree, and then visit the, I'm talking about post order, sorry. Yeah, the post order, yeah. How would you traverse in a post order way? You visit the left child, visit the right child, and then the root, right? Yeah, you get the idea. Okay, let's now have a look at that, how we can implement that, and then we'll trace the code all together. So now what we have over here is visit addition over here. So we notice that we do have another two local variables of the same type. We got eval left, eval right. So this is where the recursion can occur, which means I'm going to delegate the visiting job for the left subtree to eval left, which is just another evaluator. And I'm going to delegate the job for recursively visiting the right subtree to eval right, which is yet another visitor. In order to visit this root, I'm going to create internally two separate visitors. Basically, that's the idea. And now, how do we do that? Now, we can simply say a.left, which will be of type. What's the type for a.left? Do you need to cheat? What's a.left? A dot left does it have to be expression? It doesn't have to be addition, does it? Because it's the A dot left, the static type is simply expression over here, right? A dot right as well is also expression, right? So what we do is we can say A dot left dot accept. Again, you say accept. So we can use the accept feature where you can actually go down one level. Accept the left child, accept the right child, and then try to combine the result together. Okay, A dot left is of type expression, A dot right is also of type expression. And we can accept both of them by using eval left over here and eval right over here. Okay? And then afterwards, we can say whatever value it is for the current evaluator. Okay? We're going to combine the result for the left evaluator and the right evaluator, combine the value together, and then we get an overall value. I haven't traced yet, but any question you have, I'll take it, and then we'll trace the code together. Yeah. What feature do the composite have? Well, you tell me, what do they have? Left and right. Okay, composite. But that's only for the expression language. For the projects or for whatever you're going to do, you might define something different. In general, you can just make a list. Right? Yeah. Okay, guys, any question before I try to trace the code? No questions? Questions? I can do that. You know what? The question was, can I go over the do and then evaluate the block? I would say, let's try to chase the code. As we do it, I'll go line by line. That'll be better. Okay, if you know question here, what I would do is I will clean the diagram over here. And then we'll try to trace the code from scratch. Okay, it's much cleaner. Okay, let's trace the code. I don't need this tree, do I? Over here. Okay, let's try to trace the code. Okay. Now, what I would like to trace is this line over here. We're assuming that we already got the following startup code. This is what we assume. We already got, let me just highlight it for you. I'm assuming that we already got these lines of code to initialize the expression that we have, 1 plus 2. Okay? That's what we have over here. That's the add. And then we're trying to do add dot accept. And then what's V? V is simply an evaluator. Okay? See you next time. Oh, he didn't know that. Okay, anyway. All right. Let's now see how we can trace the code. Over here, we got add accept. Let's be a very companion machinery. Okay. Now, this another term I would like to mention to you first is something called double dispatch. Now, what double dispatch really means is dynamic binding is going to occur twice. Okay, twice. You can think about this question here. Which 2 times is it going to occur at different context? Okay, we'll get there. Okay. Now, what I want to do is like this. So now, when I say add the accept V, okay, it compiles, no problem. So now we definitely got either this accept over here or this accept over here. Which accept should we go? The one above or the one below? Below, right? That's the first dynamic binding you got. That's the first dispatch. Okay? Now, what I would say, I'll make a note over here. Because the dynamic type of add is addition.
Did you say it was the top or the bottom?
The bottom, the one below, yeah, the bottom, yeah, good. Okay, because the dynamic type of add is addition, so the first dispatch calls the accept in it, okay, which means addition. So now that means for the first dispatch, we're going to execute the accept feature over here. Okay? And now we know that we pass the V over here. Okay, the V. That means, well, this is going to be replaced by the V, which is this object over here, right? Now, apparently we got something called visit addition over here where the context object is called V, right? So now, how many visit addition do we have in our architecture? Visit constants. Sorry, visit addition. Let me just say it again. How many visit addition do we have in the architecture? 3, right? It can be either the visit addition in the evaluator, it can be the visit addition in the pretty printer, it can also be the visit addition in the type checker. So now, which one will we go? Evaluator? Why? Data type for V is actually evaluator, right? That's a second dispatch. Okay, we got 2 dispatches, right? The first dispatch depends on the dynamic type for the expression. The second dispatch depends on the dynamic type for the visitor. Double dispatch, okay? It's a very classic question to ask in the exam. Explain the double dispatch in the visitor pattern. Don't be too surprised if you see that, okay?
So this first one is going to be called by calling the accept method.
Yeah.
We'll go to visitor, and then visitor will.
Yeah, we'll get to the visitor part. Yeah, we'll get there. Okay. So now let's now talk about it. Okay. So now over here, since we are now in this context over here, so that means we're gonna call v.visit addition over here, right? And we know that at this point, v, the dynamic type is evaluator. Okay. So now that means we got a second dispatch. Now I'll put it in green. Because the dynamic type of V is evaluator, oops, that's the wallpaper on my iPad. Wow. It's not relevant, sorry. Ignore that when you watch the recording. Yeah, it is. Yeah, well, it's not important. Yeah. Dynamic type of V is actually evaluator. So that means when we are trying to call this particular feature, we'll actually go to the version that's defined over here, okay? Rather than the one for visit constant, right? Oh, rather than the version in the pretty printer or the type checker. That's what I meant, okay? So now here is the second dispatch. Calls the visit addition, visit add in it. When I say it, I mean the evaluator. Okay, that's the one. Okay, let me recap very quickly, and then we'll go into the body of the the visit addition. Let me just say one thing before I take your question. So there are 2 dispatches over here. First dispatch, you actually choose the version of the accept, which means it will be in this case the accept in addition. The second dispatch, you will choose the version for visit this particular expression in the visitor. In this case, because V is of type evaluator, so you go to visit addition for the evaluator. Okay, it's 2 dispatches.
Oh, I just want to clarify what you wrote over there. So first dispatch calls accept.
First dispatch, it calls the accept. Yes, correct.
Oh no, you wrote something beside the this.
Accept in it.
Oh, in it.
In it, yeah. Sorry, just running out of space. Yeah, I mean in it. Yeah, it's addition here. That's what I meant. Okay. Yeah. Okay, so now the thing is we have to do some recursion over here, okay? I don't want to distract too much because I presume you know more or less how recursion works. Let's try to get a big picture on that, right? The idea is, let's try to go line by line and then we'll see, okay? So now, let's try this. So now we are executing this block of code. Let's go line by line. First of all, we create 2 local variables, evaluate left and evaluate right. Let me just draw that very quickly. So that means we got eval left over here, which is pointing to some evaluator objects. Also, we got eval right, which also points to some eval objects. Okay, so we got 2 extra objects locally. Okay, and then let's go over the do block over here. The first one, a.left.accept. Again, can we try to practice double dispatch? Every time you try to initiate a call to the accept, you got double dispatch. Anyone want to try before I tell you exactly how it happens? We got two dispatches in a similar way. Anyone want to try? How about the first dispatch? So the question is, when I try to call this particular a.left.accept eval left, so what are the objects that's involved? So a.left is talking about, so A is over here, the add. A.left is talking about this particular left subtree for the expression, right? But left subtree turns out to be very easy, very simple. So A.left is this green object over here, and then we say accept eval left, which is this particular eval object over here. So now we got another instance of calling the accept feature. So the same principle about double dispatch is going to apply. Let's practice one more time, okay? How does it work? Anyone want to try? How about just try first dispatch? How is the first dispatch going to work?
That line right there. Eval left.
Mm-hmm.
So the first one calls an evaluator.
Not quite, okay, yeah. Okay, anyone want to try? If no one, I'm going to tell you the answer. It's okay. I just want to see if anyone want to try. It's complicated, don't worry, I know, yeah. How about I give you a little bit hints, okay? A little bit hints. Because if you really want to understand the issue correctly, you want to trace like this, okay? Let's say I got this line over here. Let me put it here. Let me put this line over here. A.left.accept. And then eval left. Now, question for you as a hint. What's the context object for accept? Context object.
So a.left points to a constant.
Okay.
So it's going to call the accept in the constant class.
That'll be the first dispatch. That's good. Okay, let's stop there. Okay, good. And now we'll continue. Very good. Very good. Okay, let me just say one more thing, just adding to what you just said. A.left over here is the context object for calling the accept. Right? First dispatch, we want to ask ourselves, what's the dynamic type for A.left? Well, A.left is pointing to this particular object here of type constants. So that's the dynamic type, which means for this particular application over here, we're going to call the accept feature in the accept feature over here in the constant class. Okay, that's the first dispatch. Okay, let me write it down. So what I will do is I'll do it here. Okay, first dispatch. I'll make it a little bit briefer. So it's accept in constants. You can see the first dispatch is applying the same principle, but the context is a little bit different, right? In the previous case, it's the accept in the addition class, but now it's the accept in the constant class, right? Yes. Well, you can see that over here, right? So you can see that over here when we say A.left.accept, right? So now we want to know which object is the context object for calling accept. It's whatever that's to the left of the concept of the accept, right? So that's A.left. So what's A.left? A.left, you see from the diagram, is simply pointing to this particular object for the constant. So that's a dynamic type. So that means when you apply dynamic binding, it's going to go to the accept version that's in the constant class, as opposed to other classes, right? Yep. Again, guys, this is really important if you understand, well, this will be easy if you understand dynamic binding, okay? If you're having trouble, you should speak to me after class, okay? Okay, good. Okay, that's about first dispatch, and then what happened after that? So now that means we're going into this particular accept feature over here for the first dispatch, and now we are going to call v.visit constant over here with current, okay? And now what's really v over here? V is eval left, right? Now, anybody want to try second dispatch? Yes, go ahead, second.
So second dispatch would be the evaluated class
Evaluated cost, why?
because of the evaluated.nesting
Basically, second dispatch works the following way. That means eval left is the argument over here, and we know that v over here is basically eval left. It will be replaced by call by value, right? Eval left. Eval left is going to be of dynamic type, also evaluator. That means we're going to call the visit constant feature. How many versions do we have? Visit constant. Well, can be here, can be here, can be here. However, dynamic type is simply just constant. Oh, sorry. Dynamic type is simply evaluator. So that means we'll go into the visit constant in here. Okay, similar idea. That's the second dispatch. So I would say for the second dispatch, so what we get is we'll go to the visit constant in evaluator. Okay, yep, that's the second dispatch. Now, we're going to, since this is the base case, that means things are going to terminate, no further recursion. Okay, so now that means that's the end of our illustration. Okay, so now when we do v dot visit constant and with the currents, what's current? What's current? According to the diagram, what's current here? I agree. So basically this constant here, right? Keep that in mind. So now when we switch the context to visit constant over here, right? We know that the C over here basically is the current. And that's exactly at dot left, right? That's a left child of at. So now, can we try to complete this particular line over here? So what does that mean? That means for eval left over here, it has an attribute called val, like a value. Okay, that's the attribute over here, value. That should be assigned to whatever C. What's C? C is at the left, which is over here, at the left. The value of that is simply just 1. We're going to copy that over, so that'll be just 1. So that's the result. Okay, that's the recursive result we get from the left child, from the left subtree. So now, without trying another double dispatch for the right child, I will leave that as an exercise for you. But let's try to imagine what's going to happen. When we try to call this second line over here, when we say a dot right dot accept, right? Basically following the same pattern. But now, it will be this particular right child expression to be handled, to be accepted, right? And then what we will do is, when we try to do this one here, eventually what we will get is eval right will be delegated to visit this particular expression child. What that will do is, it's going to set eventually the val for this particular evaluator to be 2, right? So that means eval left, the value will be 1, eval right, the value will be 2, and now finally we can combine them together. Over here, eval left, the value in this case is 1. Eval right, the value in this case is 2. And whatever they are, combine them together, you will see that should be the value for the current evaluator, which was the very original one, which was V. Okay? That means V over here should be set to 1 plus 2, which is 3. That's the final result. Questions? Well, actually, both dispatch depends on the dynamic type of the context object, both.
Right,
because context, yeah.
dependent on the context object.
Correct.
But essentially, we took it as first it was a context object which we took a look at, and then it was
Yeah.
an object.
Yeah.
So
Yeah, so basically every time if you want to talk about dispatch, think about what the dynamic type is for your context objects. If it's a visitor, it's an evaluator, you go to evaluator. If it is a addition, you go to addition. Depends. Yeah, well, true. Yeah. Combine them together. Okay? Yeah. Guys, let's do a visual summary very quickly. Okay? But I would suggest if you really feel it confusing, rewatch the illustration process. Really important. Okay? Let's now do a visual summary. How does the oh, this one's really a mess. Let's try to do this. Okay, now it's clean. So what I would do is, let's do a visual summary, okay? Now, how does the double dispatch work for visitor pattern? Let's see from an architecture point of view. Basically, you start with maybe add dot accept. So you start with the expression side, agree? Okay, so now, based on what the dynamic type is for the expression, you're gonna first of all choose a particular class from the expression side. For example, this will be the first one, addition. After which, you have to see internally what the accept will do is to call v dot visit addition, right? Now, which visit addition is gonna call? Well, it's going depending on what the dynamic type is for v, which can be evaluator. In that case, you go to this particular descending class. That's the second dispatch. First dispatch locates the class under the expression. Second dispatch locates the class under the visitor. Okay, that's a visual summary. Two dispatch. Questions?
Is it possible to have more than two?
Is it possible to have more than two dispatches? Try that in your projects, and then let me know. No, you don't need it. No, you don't need it. Yeah, I think double dispatch is quite nice. Yeah, yeah. Yes, questions?
So just a clarification, so double dispatch is a feature in IFO, or is it like a...
No, double dispatch, you know, I'll try to give you some reference. I kind of forget, I once read it. So there is certain programming language which support double dispatch in a single feature call. I'll try to look up which programming language it is. I'll try to look it up. I don't want to say it now in case I give you wrong information. In programming languages like a Java, C#, IFO, they don't support any double dispatch. The way you can simulate double dispatch is by having two single dispatches. That's exactly what we did, right? Because when we say add the accept, that's a single dispatch. That's the first one. And then later on when we say visit addition, that's the second one. Each individually they are single dispatch. Okay? But together it was called double dispatch because two, right? Yeah. Guys, any more questions about visitor? Yes.
You add a value here into visitor to short visitor. You don't have cost, right?
You mean the value? You mean value? Okay, let me see. You're talking about adding a feature called what? Value? In where? Visitor? You mean over here? Oh, I see what you mean. I tell you what the problem is. Good question. The question was, can we just add a value feature? You can see that the way I did it, I simply say under evaluator, I'm gonna have a value over here called integer, right? Let's say we do that, okay? Now, rather than having that, it's design choice. So why did I make that design choice? Let's discuss it. If I say value over here, integer, so what does that mean? That means every descending class of the visitor must implement this feature here. Does it make sense for example, pretty printer to have a value of type integer? Not quite, right? Also, type checker, maybe not, right? That's why. Okay? So that what the lesson is, for individual descending classes for the visitor, you should really decide what kind of features you like for that particular visitor. Maybe it can be, for example, type checker. It can be a value called type check or not, like a Boolean value, right? For maybe pretty printer, it can be a string value for the attributes. Yeah.
Some of the really cool double dispatch methods and chaining that we're doing, what's the point?
What's the point?
Is
Well,
it just another way to hide it?
not really. So what's the point of doing all these? The point is, we are now, okay, several points over here. Okay, let's talk about it, okay? So now, let me just, again, I don't want to erase this, so you can keep that visual summary. First of all, this architecture is very nice. Rather than cramming all the pretty print, type check, and evaluates inside expression, right? That we talk about the poor design, polluting your class, violating single choice principle, and also the cohesion. That's what we said, right? So point number one, this new design pattern here, which basically got composite on the left-hand side and got visitor on the right-hand side over here. The point number one, we have a separation of concerns. Concern number one, language structure. Concern number two, we got language operation, right? That's point number one. We got separation of concern. And point number two, It's more about the single choice principle. How can we satisfy that? That's something I'll just get into. Now, remember the open-close principle I talked about, right? Let's talk about open-close principle. Do I have a page for that? Yes, I do. The same architecture. Let's talk about open-close principle. Okay? So we got separation of concern, we got structure, we got also operation. Again, let's review what open-close principle really tell us. That means we have to decide certain parts to be open, certain part to be closed. What did we decide for the visitor pattern? Which part should be open? Operation, right? Good, thank you. So now the operation part should be open. So what I would do is, let's make a note. So this part here should be open, whereas this part here should be closed. So now let's see why such decision should be the case, but rather than the other way around. Okay? I got two hinting questions over there for you, the blue and the orange. So now, adding a new language construct versus adding a new language operation, which one is going to violate the single choice principle? Which one? Adding a new language construct? Why? Why is that? Yeah, okay, let's see this, okay? So now, first of all, let's be logical here. Adding a new language construct over here is going to turn out to violate the single choice principle, okay? And this means this part for the language structure should be closed. On the other hand, adding a new language operation for the visitor architecture is going to satisfy the single choice principle. That means this part can be open. That's we're trying to figure out backwards, basically. Okay? So now let's now see how the single choice principle will work for both cases. Let's talk about this one here. Adding a new language construct. Okay? What does that mean to change the architecture? Okay, Raymond, go ahead. I like that. Let's say we do that. So let's say I put a new class over here. I would say multiply, which has to be a subclass of this and that. Exactly. So that means we have to, first of all, at the deferred level to say visit multiplication and whatever the argument is. And then what is that? That will be deferred. And for every type of operation class, we have to say visit multiplication, and also visit multiplication. That indeed violates the single choice principle, right? So that means for the visitor pattern architecture we just have, that one there, this part for the language structure should be closed. Otherwise, you can easily violate the single choice principle. And for the double dispatch, it's just byproducts because we got this architecture. It's not because we want to have double dispatch, so we got this architecture. No, it's because we want to have this architecture. Double dispatch is just a byproduct. It's just a consequence of that.
Just one quick question. Are there any instances wherein adding a new language construct would satisfy single choice and adding...
For this, yeah, the question was, is it possible to really somehow modify the visitor pattern so that you will still satisfy the single choice principle by modifying the language construct? The answer is no. This is no silver bullet that will actually satisfy both aspects. Okay? Yeah. Okay, let's do the final one, another one. What about adding a new language operation? This is really critical. So now, according to what I said over here, it will satisfy the single choice principle. Let's say I want to add a new operation called, let's say, generates assembly code. Generate assembly, let's say. So what would be the step to extend this architecture here? How many classes do I need? 1? 2? Just one? Where should it go? Go to expression or go to visitor? The operation cluster, right? That means I need to create a new descendant class over here, call that maybe I'll just call that generator. How about that? Generator. And now, because this is a direct descendant of visitor, and this one should be effective, right? So now this is the only place or the single place I need to implement to say, for constant, how do I generate the code? For addition, how do I generate the assembly? So I'm going to say over here, visit constant, and also visit addition. So these are this is a single place where I talk about how to generate assembly code for the various structure, right? And all the various structure are already defined at the visitor level, okay? And that one will satisfy the single choice principle. It will be okay. Guys, any questions? I would say that's the trickiest pattern for this course. If you got through it, that's good. Okay? Yes?
Open-close principle guarantees the single choice principle.
Does the open-close principle guarantee single choice principle? I would say not necessarily. Open-close principle simply tells you that if you want to make a change, you should always make it in the open part. But when you make such change, it may still violate the principle. So I would say they're orthogonal. Yeah. Okay. Okay, guys, any more questions about this? Okay. So now let's go back to the slides. Let me see what else to say. Okay, you will see everything has been set already on the iPad. Let me see if there's anything else to add. Okay, there's a tester we have. Now, again, there's a double dispatch that I talk about, okay? When should we use the visit pattern, okay? Basically, again, you should really try to see, make sure the single choice principle is obeyed, which means you only try to add operation to a visited part. Okay, so now, this is some very nice resources for you. Last year, I created a tutorial series to actually show you how you can develop composite and visitor from scratch in iPhone Studio. You may find this useful for your projects. You may or may not, okay? Okay, but I would suggest go over that. That will also help you for the exam. Okay, we do have 10 minutes, right? Do we? Less than 10? How about I just use about 5 to 6 minutes, okay? Huh? We have 8. I'll use only 6. How about that? Okay, finally we get to voice safety. I wanted to come here about 3 weeks ago. Never got a chance. Anyway, but let's just go. I'll give you the idea quickly. Now, again, let's go back to Java. Okay? Let's consider this Java program over here. Okay? All I want you to do is follow the logic for the simple Java classes, and then I'll ask you some question. Okay? We have a point class for two-dimensional point. With two attributes, x and y, we got a constructor there with x and y, okay? Point class. And we have something called point collector. And the point collector simply declare an attribute called points of array list. Let's say we already import the array list, okay, from the library. And then we got some constructor over here, okay, just default constructor. And then we got some mutator here, which will add a points of type P points into the array list. And also, we also try to see, I want to get a point at a particular index, and then return that particular I. Let's assume I is going to be a valid index. Let's not worry about the precondition here. Okay? Now, question number 1. Does these two fragments of code compile in Java? Just compile or not? You compile? Just, just more like, of course, you're not a compiler. I'm just giving you intuition, right? Yeah. Okay, I can tell you it compiles. Okay, it does. However, if you translate the same idea into iPhone, it will not compile. Okay, that's really the essence for voice safety. Okay, we'll try to go over 1 or 2 examples. Yes?
So, this is the reason for the voice safety? Because
Yeah.
Java has applied for the time?
Yes, correct. So let me just recap, just tell you exactly very quickly. The voice safety idea is there's certain scenarios where the Java program can compile, but it can result in null pointer exception at the runtime. What IFA does is they try to make such a scenario not compilable even, which means it's going to tell you, no, you should not even try to execute the code because it's going to crash. Java compiler doesn't care. It will just let you deal with null pointer exception at the runtime. Okay? Now, let's see for this particular one, let's see some slides over here. Okay, it compiles, but what? Anything wrong? Okay, that's the next question. Anything that can go wrong. For example, let's do a test over here. Let's say we got a point collector object over here, PC, and then we say PC.addPoints, and then we simply put a new points over here, 3 and 4, and we put another point, and then we try to see get the points at position 0. Okay, we just valid index because it's only 1 point, so get the point at index 0. And then we try to assert to make sure the only point we have added should have x3 and y4, right? 3 and 4. So now, everything compiled, I can tell you from the Java side. Is there anything wrong at runtime? Line 4, okay. Line 4 where? What? Okay, that's good. Okay, anybody want to try? Maybe not everybody heard you, which is good. Okay, anybody want to try? Okay, so basically everything compiles, but there will be a null pointer exception at the runtime. Can you see exactly which line of the test over here? Line 4. Okay, okay, agree? Let's see why. What happened is when you try to do over here, line number 4, let's see for line number 3. Line number 3, what do? You simply call the point collector constructor, which is over here. Does nothing to initialize the points array list, which means after this point, PC.points will just be null. So now when you try to do PC.addPoints over here, that's okay, PC is not null. However, when you try to execute the body of this method here, add points, you will just go to points.add. What's points? It's array list. It's null. So basically you're doing null.addP, which will give you null pointer exception. Agree? Okay, so that means Java does allow certain scenarios to be compilable, but you might have null pointer exception at the runtime. Ivo would not allow this. I'm sure you have seen things like this, right? To say the variables over here, points, is not initialized, something like that. Okay, let's do one more, and then I'll let you go. How about this one here? Let's go over the code all together. And then we'll go to the remaining part for the voice safety, which will only take about 5 minutes next time. Okay. Now, another class, also we got points here, and we got point collector. Let's now, I fixed the previous error. I simply got points is assigned to new array list, just empty to begin with. Okay. Now let's say got test2. Point collector objects, and then I simply assign that to null. And then I do it immediately after this. I say PC.addPoints P. Okay. And then P is assigned to PC.getPoint at 0. And then I will assert true, P.x is 3 and P.y is 4. Everything still compiles. However, Java side compiles, but it's going to give you runtime null pointer exception. But which line? 6? Well, if you say 6, what's wrong with 6? 6 over here, we're going to say PC. Okay, let's just go to the iPad over here. Line number 6 over here, let's see if there's really going to be an issue. So line number 6, you say PC itself is not null, right? We agree. Okay, PC is okay. It's just a new objects. Get point at position 0. Get point at position 0. What's wrong with that? But points over here is initialized, so nothing wrong with that. Last line? Yeah, last line, right? Because remember, here we simply say P is assigned to null. Remember, Java compiler does not keep track of the runtime values for you. In principle, it's undecidable. Okay? Now, line number 4 is simply null. That means we're adding simply null into it. So now when we are retrieving this particular get point, P here will be null. P.x will be 3. You think? No. P is null. Null.x will be null pointer exception. Make sense? Okay? Okay, okay, you are ready to go. Okay, I'll see you on Thursday. All right.